Our last section of chapter 3 is the only one that involves any math for this chapter, but we are coming back to this idea of conversions again. So our aim for section 3.6 is to understand energy and its effect on matter. So here we're specifically looking about heat energy and how heat energy contributes to changes in states of matter. We need to remember that energy is the capacity to do work, and there are different types of energy, but here we are talking about heat energy being supplied to a sample. We use the term calorie here, and calorie is the amount of energy or heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So it's the amount of heat energy that I would need to raise the temperature of 1 gram of water by 1 degree Celsius. And it's hard to imagine what 1 gram of water would look like, but we know that water's density is 1 gram per cubic centimeter. Or remember, that's the same thing as 1 gram per milliliter. So you might be able to envision 1 milliliter of water, but it might be easier for you to now envision 1 cubic centimeter. So remember, a centimeter is approximately like that. So if we have 1 cubic centimeter, now my drawing is not totally accurate, but we're talking about a sample of water that's 1 cubic centimeter, 1 centimeter by 1 centimeter by 1 centimeter. So if I had a sample of water that large, and it had a mass of, we know it will have a mass of 1 gram, a calorie is the amount of heat required to take that sample of water and heat it up by 1 degree Celsius. Now, this is a little bit different than the calories you know of as food calories. So the food calorie is actually 1 kilocalorie, or 1,000 of those little calories. Remember, kilo means 1,000. So we differentiate between little calorie and big calorie by saying big C and little c. The big C, or a kilocalorie, is what you would see on your food labels. And I believe in European countries, they actually use kilocalories instead of big calorie like we use here. So you can see not a whole lot of caloric content in this sample. We're talking about sucralose, so we're probably looking at something like Splenda in this case, which isn't a good example, but this was just showing you where you're going to find that big C and what that big C means. So if you eat something that has 100 calories in it, that actually refers to 100,000 calories. The SI unit of energy is known as the joule. So we use calories, but joule is the SI unit. So we have to be able to convert back and forth between the two. We know that 1 calorie, small c, is equal to 4.184 joules. Now we're not going to use big C again. I was showing you how that compared to what you'd see in your food labels. So we're talking about small calorie here. 4.184 joules is 1 calorie is our equivalent statement. So remember, every equivalent statement gives us 2 conversion factors, 4.184 joules per calorie or 1 calorie over 4.184 joules. And which one we use is determined by what we're starting from and what we need to convert to. Because remember, we want to make sure that whatever unit is on the bottom is the one that we want to cancel out. So if I'm asking you, how many joules are in 60.1 calories? We follow the same format we've done with all of our other conversion type problems. We start with our given piece of information, which is 60.1 calories. And remember, we're multiplying that by a conversion factor. We draw our line, and on the bottom of our line, we're going to put calories. And remember, we're doing this so calories can cancel out because we don't want to end up in units of calories. We want to end up in units of joules. We know because of our conversion factor that 1 calorie equals 4.184 joules, that we can convert directly between calories and joules. Just so happens in this case that we're putting calories on the bottom so that they can cancel out the units. So when we do this, this becomes multiplication. Remember, we can ignore any ones in dimensional analysis, and the numbers across the top are 60.1 and 4.184. When we multiply those together, we get 251.454. Numbers mean nothing without their units, so we have to put a unit on the end here, and that unit is joules. But we have to observe sig figs here as well. So remember, conversion factors never guide our number of sig figs because conversion factors are said to be followed by an infinite number of sig figs. So we're just looking at the first number, and our first number has 3 sig figs. It's got 2 non-zero digits, and then it's also got a captive 0. So that gives us a total of 3 sig figs. So we need to make sure we have 3 sig figs in our answer. And then to make this answer complete, we have to put the joule unit on the end of it. So anytime you're circling your final answer, you need to make sure that you're circling the one with the correct number of sig figs and the correct unit on it. If you're circling this one has the correct unit, but it does not have the correct number of sig figs. So that would not get full credit. Take a minute, complete this practice. I've given you a couple of conversion factors that you're going to need. Remember, 1 kilojoule is equal to 1,000 joules, and 1 kilocalorie is equal to 1,000 calories. So stop this video, do some practice in your note packet, and then resume the video and we'll go over the answers. In our first problem, we've been asked to convert 124,567 kilocalories to joules. So our first step in a problem like this is to write down the number we've been given, 124,567 kilocalories, and then we want to do our conversion. We're going to convert from 1 kilocalorie to 1,000 calories, and then we're able to convert from 1 calorie to 4.184 joules. So then when we put this into our calculator, we have all ones in the denominator. So we're able to just multiply straight across the top. 124,567 times 1,000, and you can just use the calculator on your phone to do this, times 4.184. And this gives me 521,188,328. So we want to use sig figs and scientific notation to represent what we have here. That answer would end up being 521,188 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 8th. Remember, the mantissa needs to include all of your sig figs. So this would be our correct answer. For the second one, we're starting with 0.435 calories, and we're converting that to kilojoules. So we're going to put calories on the bottom, joules on the top, and we know for every 1 calorie we have 4.184 joules. And then we can convert from joules because we know that there are 1,000 joules in 1 kilojoule. And in this case, again, putting this in your calculator, you're going to enter 0.435 times 4.184. Those numbers are both on the top. And then you're going to divide by what you see on the bottom. So 4.184 divided by 1,000. And this gives us a final answer of 1.82 times 10 to the negative third. And don't forget your units. We have the unit of joules on the first answer, and we have the unit of kilojoules on the second answer. Now for the third one, we're starting with 0.005 kilojoules, and kilojoules and kilocalories have the same relationship as joules and kilojoules, and I'll show you why. I'm sorry, as joules and calories. So if we're converting, we're going to go from kilojoules to joules. So we know that this is 1,000 joules to 1 kilojoule. And then we can convert from joules to calories. 1 calorie is 4.184 joules. And then we can convert again from calories to kilocalories because we know that there are 1,000 calories in 1 kilocalorie. But what's happening here is you can see we have 1,000 on the top and 1,000 on the bottom, and those will cancel themselves out. So really what we're able to do is convert directly from kilojoules to kilocalories because they have the same relationship as joules and calories. So in this problem, we're taking 0.005 and we're dividing that by 4.184, and this gives us 0.001953. But if you notice, our initial number only has one sig fig, so we only need one sig fig in this final answer. And if we do that, we're cutting it off right here. The 9 rounds the 1 up to a 2, and we end up with 0.002 kilocalories for our final answer. The third one, let's try our shortcut here because we know we can go directly from kilocalories to kilojoules. So if we're starting with 900 kilocalories, we can convert directly from kilocalories to kilojoules using the same conversion as we did between joules and calories. So we know 4.184 kilojoules to 1 kilocalorie, and then we can multiply here 900 times 4.184. This gives us 3,765.6. Again, one sig fig in my answer. So this would actually round this number up to 4,000 kilojoules. As long as I don't put a decimal point in that answer, only the 4 is significant. And the last one, 650 joules. And this is just asking us to convert from joules to calories. We know we can do that because 1 calorie is 4.184 joules. So here we're dividing 650 by 4.184, and this gives us 155.35. Here we need 2 sig figs, so that means the answer would be 160 calories. Now in the last part of this section, we're going to look at a sample problem, and this sample problem asks us to determine the amount of energy in joules required to raise the temperature of 7.40 grams of water from 29 degrees Celsius to 46 degrees Celsius. There's a lot going on in this problem, so we need to introduce a new equation, and this equation is Q equals mc delta T. Now, in using this equation, you see we have all of the information we need to be able to solve for what the question is asking for. And in this case, it's asking for the amount of energy. So the first thing we need to do is to define each of these variables. Q represents energy, or in this case, heat, in terms of the unit joules. M, we've probably seen this before. This is mass, and remember, mass is in units of grams. C is what's known as specific heat, and specific heat is in units of joules per gram degree Celsius. So we already looked at this in terms of the calorie and then how that converts to joules. So we'll look at that again in a second. This unit, a lot of people want to mess with that unit by doing extra division. Don't worry about that. The unit is a unit that's already on the number we're going to use, so you do not have to do any division. This problem is set up in a way that all you have to do is plug in your variables, and I will show you in a minute how that works. Delta T, this delta symbol refers to a change, and T is temperature. Now, this change in temperature is most often given in degrees Celsius, but remember we did talk about how a jump in the Celsius scale is the same as a jump in the Kelvin scale, which means I could also be referring to a change in temperature in terms of Kelvin here. Celsius and Kelvin will both work. A change in Fahrenheit will not work in this position because that is not equivalent to a change in Celsius or a change in the Kelvin scale. So again, looking at this problem, we want to be able to define all of the variables we have and also define what we don't have. So we know the following pieces of information. We know they're asking us to solve for Q because they're asking us to determine the amount of energy, and we know energy is Q, so that's our X. That's what we're solving for. We know M is 7.40 grams as given in the problem. C, we know the units, but we also know the number because here we're talking about water. So we know in the definition of calorie, we're talking about the energy required to raise 1 gram of water by 1 degree Celsius, and that's exactly what we see right here. So if we're converting between calories and joules, This value allows us to do that. This value is a constant. So for water, C will always be 4.184 joules per gram degree Celsius. If we're dealing with a different substance and I ask you to use a specific heat of that substance, I will let you know what that specific heat is. But for water, you do need to know that that value is 4.184. So if you see H2O or water, that's the value you're going to use for C. And then a change in temperature, they give us the low temperature of 29 and they tell us it was raised to 46, which means the change in temperature is 17 degrees Celsius. So now we've defined all our variables, we know what we're solving for, we just have to plug in these values. So this is our M, 7.40 grams. This is our C, and notice I haven't done anything weird with the units here. All I've done is plugged in that number and the units stay the same. We know the units cancel out because if we arrange it in this way, we have grams, we have joules per gram degree Celsius, and then we have degree Celsius. We know all of these are multiplied together. We know degree Celsius cancels out, and we know grams cancel out, and we're left with joules. So we have our change in temperature. We're left with joules. Once we put all of these in our calculator, 7.40, 4.184, and 17 degrees Celsius, all we're doing is multiplying because all of those are in the numerator anyway. We get the number 526.347 joules. But remember, if we're observing sig figs here, we're going by the fewest number of sig figs because we're looking at a multiplication problem. 7.40 has 3, 4.184 has infinite because it's a conversion factor, and 17 has 2. So we need to use 2 sig figs in our answer. Take a minute, pause your video, complete this problem, and then we'll come back and look at the answer. In this problem, again, we should recognize that we're using Q equals MC delta T. And again, we want to define our variables. We know that M is 1.3 grams as given in the problem. Our specific heat was given to us in this problem, 0.45 joules per gram degree Celsius. Again, don't get hung up on the unit. Just plug that number in for C. Delta T, we're looking at a change from 25 degrees Celsius to 46 degrees Celsius, which is a change of 21 degrees Celsius. We've already seen how the units cancel out here, so we know if we're solving for energy in joules, that our final answer will have a unit of joules. So let's look at sig figs. We have 2 in our mass number, 2 in our specific heat number, and 2 in our temperature number. So we're going to end up with 2 sig figs in our final answer. So the answer comes out to 12.285 joules. Rounding to 2 sig figs gives us a final answer of 12 joules.